Beneath the quiet, dark star colours are never just decoration. Some stars glow deep red like embers, others shine blue-white like frost. And sometimes the same light looks warmer simply because it has travelled farther, slipping through dust or stretching with the expanding universe. In this story, the sky becomes a calm palette with hidden rules. Temperature, absorption, scattering and distance all leave gentle fingerprints on what the eye receives. If this kind of slow science helps the mind unwind, please tap like and subscribe for more long-form cosmic sleep documentaries. Now let the colours settle. Let the light do the explaining. Star colour seems like decoration at first. Most star colours track surface temperature, then dust and gases bend the result. In a quiet field of points, one light looks blue-white, another looks deep red, a third looks amber, as if a veil lies between the source and the eye. The first unlock is simple and steady. A star's surface glow follows a thermal spectrum, which means light spreads smoothly across colours. Hotter surfaces lean toward shorter wavelengths, cooler ones lean toward longer wavelengths. The scene holds on a single stellar disk where brightness is not uniform. The centre looks fuller, the edge looks softened. A gentle gradient appears from centre to limb because the line of sight skims higher and cooler layers. That physical shading matters. It changes the impression of colour even before any dust enters. The next unlock comes from a calm rule of thumb. Blue-white usually means the surface is hotter. Deep red usually means the surface is cooler. Yet colour is never a single knob. Colour is a blend of temperature and filtering. At this distance, light behaves as a long message. The message passes through layers. Each layer edits the message in its own way. The surface sets the base. The atmosphere carves fine notches. Dust tilts the whole slope. The view slows near the surface itself. The photosphere shows a patchwork of cells. Brighter patches sit beside darker seams. Boundaries drift and reshape. A small change in temperature across those cells shifts the balance of blue and red light. The disk looks like a slow simmering liquid seen from above. The second unlock lands quietly. Even when the average temperature stays stable, local texture changes the colour at the edges. The thermal spectrum can be pictured without any sharp lines. It resembles a long sheet of paper that fades from darker reds into pale tones. A term helps and then steps aside. Blackbody glow means thermal light from a hot, dense surface. Like warmed ceramic, the hue shifts as heat rises. The change is not a single colour switch. It is a gradual drift of where the glow is strongest. The reason it matters is practical and deep. A star's temperature sets its pressure balance. It also sets which atoms stay calm and which stay ionized. The scene widens from a single disk to a small group of stars that share a region. Some points look icy, some look ember-like. The third unlock arrives with one safe number. A sun-like surface sits at about 6,000 Kelvin. That is far beyond the hottest kitchen oven setting. The comparison is not about cooking, it is about scale. Everyday heat lives in thousands of Kelvin at most. Stellar surfaces begin where familiar heat ends. That single number anchors the palette. Higher than that, the glow shifts toward blue-white. Lower than that, the glow slides toward red. Yet the eye can still be fooled. The eye does not read the full spectrum evenly. It emphasizes certain bands. It also adapts to darkness. A small bias can make a star look whiter or redder than its true slope. The next visual anchor forms as a calm wedge of light. A faint ribbon stretches away from the star. Its blue side thins first with distance. Its red side survives longer. This happens even in empty-looking space because space is rarely empty. Dust grains float between stars. Their sizes often match the scale of visible wavelengths. That match is decisive. Shorter wavelengths scatter more efficiently. Blue light is diverted away. Red light travels straighter. The fourth unlock settles as a single effect with a clear shape. A dust sheet does not dim every colour equally. It tilts the spectrum, it reddens the light. The star itself does not change. The path changes. A slow analogy keeps it gentle. A beam passing through a thin layer of chalky haze looks warmer at the far end. The beam loses crisp blue first. The same principle holds across light years. A scale shift arrives without strain. A dust grain can be smaller than a single cell. Yet a sparse cloud of such grains can tint the light from a star across distances that swallow entire systems. The view lingers on the dust as a faint gradient in darkness. It is not a wall. It is a mist with denser filaments. Some lines look darker because they block more blue. Other lines look pale because they scatter light sideways. The fifth unlock follows from this geometry. Two stars with the same surface temperature can look different. One sits behind more dust. One sits behind less. The difference mimics a temperature change. That is a quiet trap for intuition. It creates a limit of observation that stays soft but specific. Colour alone cannot separate heat from dust. A measured spectrum helps, yet even a spectrum has limits. If the light is faint, fine details blur into noise. If the dust is patchy, the reddening varies across small angles. If the star is unresolved, the disk texture is lost. A single colour becomes an average. That average hides gradients and hides narrow absorption notches. The mind wants one cause. The sky often holds several causes at once, or the next visual anchor returns to the stellar limb. The edge looks dimmer and slightly warmer in tone because higher layers are cooler. That limb shading can be mistaken for dust. The sixth unlock clarifies the roles. Temperature sets the overall shape of the spectrum. Dust tilts the shape by stealing blue more than red. Gases in the outer layers carve selective gaps. A term can appear once and then vanish. Absorption lines mean missing wavelengths removed by atoms or molecules, like tiny bites taken from a smooth ribbon. The lines matter because they reveal composition, yet they rarely dominate the broad colour impression unless the bands are wide. The scene steadies on a deep red star. The surface looks swollen and soft-edged. Darker patches drift like slow shadows. The redness comes from cooler glow. It can also deepen if molecules form in the outer atmosphere. Those molecules block wide swaths of shorter light. The seventh unlock arrives as a calm correction. Deep red does not always mean extreme coolness. Deep red can also mean stronger filtering. Dust can do it. Molecules can do it. The colour is a mixture of origin and journey. At this distance, light behaves as a story written on a slope. The slope points to temperature. The edits along the way point to dust and gas. The ending of this section settles the promise. The next step maps the thermal slope more carefully. It shows why blue-white feels sharp and why red feels soft. It also sets a calm ledger for separating heat from filtering in later sections. A star's colour settles into a place when the shape of its glow becomes clear. The broad shape comes from thermal emission, and the peak of that emission slides with temperature. At this distance, light behaves as a smooth hillside. The hillside leans toward blue-white when heat rises. The hillside leans toward deep red when heat falls. The first quiet unlock is that colour is not paint. Colour is a summary of how much light exists at each wavelength. The scene begins close to a calm, stellar surface. Bright granules drift beside darker lanes. Their boundaries curve and dissolve. The disk shows a gentle centre brightening and a softer limb. A thin gradient appears because the line of sight meets cooler layers near the edge. That physical gradient already nudges the average hue. It does so even before any dust or gas edits the beam. The next unlock arrives as a stable rule. Thermal emission forms a continuous spectrum. The spectrum has a peak. The peak shifts towards shorter wavelengths as temperature increases. Single term appears and then steps aside. VN shift means the peak wavelength moves shorter when temperature rises. The definition stays brief. The idea becomes visual at once. A ribbon of glow changes character without a hard boundary. The red side stays broad and heavy. The blue side becomes taller as heat climbs. The reason it matters is simple. The peak position sets the perceived colour when other filters are mild. A slow visual anchor forms without tools. In a dark cavity of space, starlight fills a faint cone. The cone fades outward. Its inner core looks pale. Its outer haze looks warmer. The shift is not a new substance. It is a change in balance. More blue photons sit near the source when the surface is hot. Fewer blue photons sit near the source when the surface is cool. A small payoff follows. Two stars can share equal brightness at one colour band. Their total energy can still differ. The spectrum shape carries that difference. The journey moves to an everyday analogy that stays natural. A fresh lava flow glows orange. As cooling spreads, the glow deepens to red and then dims. The change resembles a sliding emphasis rather than a switch. The analogy is not about heat that can be touched. It is about how a spectrum rebalances. The next payoff lands as a clear constraint. The eye sees only a narrow window of wavelengths. Much of the spectrum sits outside that window. A hotter star can emit strongly beyond visible blue. A cooler star can emit strongly beyond visible red. The visible colour can hide that extra light. A scale shift arrives gently. The surface pattern spans distances larger than entire worlds. The wavelength that shapes colour is smaller than a dust grain. Both scales coexist in one glow. The scene slows along the limb again. The edge darkens because the view skims higher layers. Those layers are cooler and thinner. The limb therefore tilts slightly warmer in tone. The disc carries a soft ring of shading. That ring is not a line. It is a smooth slope. A small payoff follows from this ring. A star can look less blue than expected near its edge. The average colour depends on whether the disc is resolved or blended. When the disc is unresolved, the ring merges with the centre. The final impression becomes a single point colour. The next anchor moves outward into a sparse medium. A faint sheet of dust lies across the line of sight. The sheet has filaments. The filaments have a gradient from dense to thin. Light crossing them loses more blue than red. The broad spectrum still remains broad, yet its slope tilts. A subtle unlock follows. Thermal shape and dust tilt can imitate each other in simple colour measures. A cool star without dust can match the visible colour of a warmer star behind dust. That is the first limit of intuition. Intuition tries to read temperature from redness alone. The sky allows multiple paths to the same redness. The second limit is a limit of observation. If a signal is measured only in two wide colour bands, the full slope is not known. Narrow features can vanish into the bands, the peak can be misplaced. Dust can be mistaken for temperature. The error is not dramatic, it is quiet and persistent. The next checkpoint clarifies what helps. A full spectrum across many wavelengths reduces the ambiguity. It shows whether the slope is smooth. It shows whether the slope is merely tilted. It shows whether wide molecular bands bite into the blue side. The narrative remains calm. No single measurement is perfect. Some information always stays inferred. A new visual anchor arrives. The star sits behind a thin mist that is not uniform. The mist forms a soft edge shadow on the background glow. The shadow is deeper in blue and lighter in red. This colour-dependent shadow is the signature of scattering by small grains. A small payoff follows. When the shadow deepens evenly across colours, the dust grains are larger or the cloud is thicker. When the shadow deepens mostly in blue, the grains sit near visible size. That statement stays order of magnitude safe. It needs no formula. It turns into an image. The blue light takes more detours. The red light keeps a straighter path. A scale shift arrives again. A single grain acts on a single photon. A cloud acts on a stream that travels for years in transit. The change accumulates without violence. The scene returns to the stellar surface for a final checkpoint. Thermal emission sets the baseline. The baseline is a smooth hill with a moving peak. The peak drift explains why hotter stars feel blue-white. The peak drift explains why cooler stars feel red. Dust and outer layers then reshape the hill. They can tilt it. They can carve broad troughs. They can warm the visible impression without changing the source. The closing transition stays gentle. The next step moves toward the blue-white end where the slope steepens and the contrast grows stronger. It also prepares for the quiet role of thin gases that remove selective colours. Blue-white starlight feels clean because the spectrum leans hard into shorter wavelengths. The same temperature shift that moves the peak also changes contrast and edge sharpness in the visible band. At this distance, light behaves as a steep slope. The slope rises quickly on the blue side when the surface is very hot. The first unlock is that blue-white is not only a hue. Blue-white is a pattern of distribution. The visible band receives more energy per step toward blue. That makes the light seem crisp. The scene begins with a hot star as a small intense disk. The center glows almost uniform. The limb fades into a thin pale rim. A smooth brightness gradient stretches from center to edge. The gradient is gentle. It still shapes perception. A disk with a bright core and dim edge looks more defined than a disk with a soft spread. The next unlock follows from how the spectrum changes. When the peak sits near or beyond the blue end of visibility, the visible band samples the steep side of the curve. Small shifts in temperature then create noticeable shifts in perceived color. The eye reads that steepness as whiteness turning toward blue. A slow visual anchor forms as a faint halo around the star. The halo is not a separate object. It is the star's own scattered light in nearby thin gas and dust. The halo fades outward with a smooth gradient. The inner halo looks cold and pale. The outer halo looks slightly warmer as blue thins first with distance. The first small payoff lands. Blue-white stars can look more sensitive to small filtering. A thin veil that barely changes a red star can noticeably warm a blue-white star. The reason is slope. A gentle, everyday analogy carries the idea. A thin grey cloth, laid over a bright white lamp, changes the lamp's colour quickly. The same cloth laid over a dim orange ember changes less. The cloth is the same. The source spectrum is different. The analogy is about contrast. It explains why a small loss of blue matters more when blue dominates. The journey moves closer to the surface texture. Hot stars can have smoother-looking disks in the visible, because the contrast of surface patterns can be subtle at these temperatures. Yet the limb shading remains. The edge is cooler and dimmer. The disk, therefore, holds a soft ring. The ring is not a line. It is a continuous drop in intensity. The second payoff arrives. That ring can shift the perceived colour across the disk. The centre looks bluer. The edge looks whiter. When the disk becomes a point, these regions blend. The blended colour depends on the balance of centre and limb. A scale shift follows without strain. The limb gradient forms across distances larger than many planetary orbits. The photons that encode that gradient have wavelengths smaller than a grain of smoke. Both scales sit inside the same calm light. The narrative deepens with a second concept. Scattering by the small dust grains preferentially redirects blue light. This makes distant hot stars appear less blue and more white, or even slightly yellow. A physical detail holds steady. In a thin dust lane, the background field shows a smooth colour gradient. Stars behind the denser filament look warmer. Stars behind the thinner region look colder. The filament has no sharp edge. It has a feathered boundary that fades from opaque to transparent. The third payoff lands. A hot star can appear ordinary when seen through enough dust. Its spectrum still peaks at short wavelengths. The visible band has been trimmed. The remaining light looks less blue. It looks calmer. That result does not mean the star cools. It means the path edits the light. The next checkpoint introduces one safe number. A very hot star can have a surface temperature around 20,000 Kelvin. That is several times hotter than a sun-like surface. The comparison stays simple. The shift is like turning a modest flame into a bright arc of heat. The point is not danger. The point is how the spectrum moves. At that temperature, much of the star's energy sits outside the visible range. The visible light is a sample of a broader distribution. That brings a limit of intuition. A blue-white star can radiate enormous energy while not looking dramatically brighter in a single band. The mind wants brightness to track total output directly. The spectrum refuses that simplicity. A limit of observation follows and stays specific. Colour, judged by a single camera band, can mislead. A band might saturate. A band might miss the peak. A band might include scattered halo light that is not from the surface. If the star is unresolved limb shading cannot be separated from dust reddening. If the medium is patchy nearby, stars can share the same temperature yet show different colours. The measurement then becomes a blend of source and path. The scene slows into a quiet wedge of space between two dust filaments. The hot star sits behind the clearer lane. Its light looks sharply blue-white. A neighbouring line of sight passes through a denser veil. The same class of star there looks pale and warm. The fourth payoff arrives. The difference between these 2 points is not a different physics inside the star. It is a different physics between the star and the observer. The difference can be mapped by the gradient along the filament edge. Where the edge is feathered, the colour shift is gradual. Where the edge is sharper, the shift is quicker. That physical edge quality hints at grain distribution. The journey returns to the star itself for a final deepening. In hot stars, the outer atmosphere can be ionized. Ionized means electrons are stripped from atoms. This changes which wavelengths are removed by absorption. The definition stays brief. Ionized means atoms lack some electrons. The example stays plain. A different set of absorption notches appears. The reason it matters is calm. The notches can change the detailed colour balance within the visible band. They can also change how white the light looks. Yet the broad reason for blue-white remains thermal. The close of the section stays soft. Blue-white light is a steep spectrum in the visible. It is also a sensitive canvas for thin veils of dust. The next step turns toward the red end where cool surfaces allow molecules to shape broad bands. The transition remains gentle. No new mystery is opened. Deep red starlight carries a softness that often begins at the surface. The main reason is cooler thermal emission, then broad molecular absorption can deepen the red even further. The first unlock is calm and direct. Redness can come from lower surface temperature. Redness can also come from wide bands that remove blue and green light. The scene begins close to a swollen red star. The disk looks large and gentle. Darker patches drift across a brighter background. The boundaries between patches are soft. The limb fades into a warm rim. A smooth gradient runs from the centre to the edge. That gradient forms because the line of sight reaches higher and cooler layers near the limb. The colour therefore shifts slightly across the face. The next unlock follows from thermal shape. When the surface is cooler, the spectrum peak slides toward longer wavelengths. The visible band sits on a different part of the curve. More of the visible light comes from the red side, less comes from the blue side. A single safe number anchors the idea. A cool giant can sit near about 3000 Kelvin. That is cooler than a sun-like surface by roughly a factor of 2. The comparison stays every day. It is like the difference between a bright kiln and a gentler furnace glow. The point is not touch. The point is how the spectrum rebalance changes colour. A slow visual anchor forms around the star. A faint shell of gas and dust expands outward. The shell is not a hard edge, it is layered. The inner layer looks denser. The outer layer looks thinner. A dim reddish haze follows the star like a soft halo. The first small payoff lands. Cool surfaces allow molecules to survive in the outer atmosphere. Those molecules can absorb wide swaths of light. That absorption deepens the red. A term appears once and stays brief. Molecular bands mean wide wavelength ranges removed by molecules. The example stays simple. A soft filter can darken multiple colours at once. The analogy stays new and gentle. It resembles adding a thin layer of cocoa powder to warm milk. The mixture becomes deeper in tone without a sharp boundary. The reason it matters is clear. The star's colour begins to encode chemistry, not only heat. The journey moves along the atmosphere in layers. Near the photosphere, atoms dominate. Higher up, temperature and density drop. Molecules can form there. The atmosphere becomes a stack of faint strata. Each stratum has its own opacity. Some strata absorb more in blue and green. The physical detail shows as a subtle ring. A darker annulus appears near the limb in certain colours. The annulus is a shadow of absorption along a longer path through the atmosphere. The second payoff arrives. The same star can look redder at the edge than at the centre. The reason is geometry. The line of sight at the limb passes through more absorbing material. That longer path removes more of the shorter wavelengths. The disk therefore has a quiet colour gradient. When unresolved, that gradient blends into a deeper overall red. A scale shift follows without strain. The molecules act on wavelengths smaller than dust grains. The absorbing layers stretch across distances larger than many planetary orbits. The effect accumulates in brilliance. Photons cross those layers for only moments within the star's neighbourhood. Yet the colour impression persists across journeys that last years in transit. The next checkpoint adds a limit of intuition. A deep red star does not guarantee a low temperature alone. Broad absorption can mimic cooler thermal emission in simple colour measures. Dust can also redden the beam. The mind wants a single cause. The sky offers layered causes. A limit of observation follows and stays specific. If the spectrum is measured in wide bands, only molecular bands can be hidden. A single red band can include both true surface glow and absorption-shaped light. If the star is faint, noise can wash out the shallow slopes. If the disk is unresolved, limb gradients cannot be separated. The measurement then becomes an average. That average can place the star on the wrong temperature scale. The scene slows into a quiet region where two red stars sit near each other. One shows a smooth, warm glow. The other shows a deeper, wine-like tone. Both appear calm, yet their reasons differ. The third payoff lands. The smoother red often reflects mostly temperature. The deeper red can signal broad molecular absorption. The difference can be sensed by how quickly the colour changes with small shifts in wavelength. A smooth thermal curve changes gradually. A banded spectrum changes in wider steps. This remains descriptive and safe. No sharp numbers are needed. The narrative deepens with a second physical anchor. The expanding shell around the cool star carries dust that forms in the outflow. The dust does not appear as a wall. It appears as a layered veil with filaments. The filaments create faint shadows. The shadows are stronger in blue than in red. That adds a second reddening effect on top of molecules. The fourth payoff arrives. Molecules shape colour inside the star's atmosphere. Dust shapes colour outside the atmosphere. Together they can produce a deep red that feels heavier than temperature alone. The effect is a quiet stacking. One filter sits on top of another. Yet the baseline remains thermal. Without a cool surface, the molecules would not persist. Without a flow, the dust would not form and drift. The closing transition stays gentle. Deep red light is therefore a blend of cooler glow and broad absorption, sometimes with dust in the near surroundings. The next step turns toward dust itself as a travelling filter. It shows how the same star can appear pale amber or brick red depending on the path. A star can keep the same surface temperature and still change colour in the sky. The reason is dust, which tilts the spectrum by scattering blue light more than red light. At this distance, light behaves as a long path that gathers quiet edits. The first unlock is simple. Dust does not need to be thick to redden a star. Dust only needs to sit in the right size range to redirect short wavelengths efficiently. The scene opens in a dark corridor between two faint clouds. Starlight crosses the corridor as a pale beam. Along one edge, the beam looks slightly warmer. Along the clearer lane, it looks colder. The boundary between lanes is not sharp. It is feathered. The feathered edge creates a smooth gradient of colour across the field. That gradient is a physical signature. It shows that the filtering grows gradually with column density. The journey moves closer to the dust itself. The grains are not visible as single points. Their effect appears as a dimming and a reddening. A term arrives once and stays brief. Extinction means dust removes and scatters light along the path. The definition stays short. The example turns into an image. A thin veil reduces brightness and warms the hue. The reason it matters is calm. Extinction can mimic a cooler star by changing colour without changing the source. A slow everyday analogy carries the mechanism without strain. It resembles white paper seen through a thin layer of tea. The paper is unchanged. The path adds a warm tint. The analogy remains gentle. It avoids the idea of paint. It focuses on how short wavelengths are suppressed more. The first small payoff lands. The same dust that reddens can also make the sky background look uneven. A field of stars can show stripes of colour. The stripes trace dust filaments. The filaments act like soft-edged brushes that do not touch the stars. They only touch the light. The next visual anchor forms as a dark lane with a glowing rim. The lane looks like a quiet river of shadow. Its edges look slightly luminous because scattered light fills them from the side. The rim is not a hard border. It is a gradient. That gradient reveals that dust is clumpy. Some regions have more grains, some have fewer. The second payoff arrives. When the rim glows, scattered blue light is being redirected into the line of sight from nearby directions. The direct beam from behind is reddened. The sideways scattered light can be bluer. Both components blend. This blend can make stars near the lane edge look oddly pale compared with stars deeper behind the lane. The impression becomes complex while the physics stays simple. Dust splits light into direct and scattered components. The journey reaches one safe number. A typical dust grain can be about 1 micron across. That is about the size of a fine smoke particle. The comparison is everyday and calm. The scale shift follows at once. A grain that's small can influence starlight that crosses distances measured in light years. It does so by interacting with wavelengths comparable to its size. No formula is needed, the match of scale is the key. Shorter wavelengths are deflected more, longer wavelengths pass more cleanly. The third payoff lands. A small change in dust column can change blue-white stars quickly. Their visible spectra sit on a steep slope. A slight loss of blue makes the remaining light look whiter and warmer. Cooler red stars can change less in perceived hue under the same dust. Their visible slope is gentler. The dust still dims them. The colour shift is subtler. The next checkpoint adds a limit of intuition. Dust reddening can be mistaken for age or temperature. A deep red point can be a cool giant. It can also be a hot star behind dust. The eye cannot decide alone. The limit of observation becomes specific. If only 2 broad bands are measured dust and temperature can overlap, the degeneracy is a real measurement problem. It is not just a mental habit. A spectrum across many wavelengths helps. Even then, limits remain. If the dust properties vary, the reddening law changes. If the medium is patchy, nearby sight lines differ. If the source is unresolved limb gradients blend with dust gradients, a signal would then carry mixed information. The scene slows into a layered dust sheet. The sheet is not uniform. It shows filaments like faint threads. Each thread has a darker spine. Each spine fades outward. The colour of background stars changes smoothly across those fades. The fourth payoff arrives. The smoothness implies that dust is distributed continuously on the sky. It is not a set of hard curtains. This continuous distribution explains why star colours can change across small angular steps. One point source can look amber. Another nearby can look white. The difference is the path, not the source. The narrative deepens with a second dust effect that stays within the same concept. Dust also absorbs some light and turns it into heat. That absorbed energy is not seen in the same band. It is removed from the visible message. The consequence is simple. Extinction both dims and reddens. Dimming alone can be mistaken for distance. Reddening can be mistaken for coolness. Together they create a layered ambiguity that only broader spectral information can untangle. The fifth payoff lands gently. A star's true colour can be recovered in principle by modelling the dust along the path. Yet the model needs assumptions about grain sizes and composition. Those assumptions are rarely perfect. That is another limit of observation. The correction is never absolute. It is a best fit within uncertainty. The scene returns to the corridor between the clouds. The same star appears twice in memory. In the clear lane it looks crisp and pale. Along the dust edge it looks honey warm. The star has not changed. The corridor has changed. The final transition stays soft. Dust is now established as a path filter that tilts spectra and creates gradients. The next step moves into the finer edits made by thin gases. Those gases remove selected wavelengths and carve structure into colour without changing the overall tilt. Colour can change without dust when a thin gas layer subtracts selected wavelengths. The main effect is absorption that carves narrow and sometimes broad gaps into an otherwise smooth spectrum. At this distance, light behaves as a ribbon with tiny missing threads. The first unlock is clear. A star's surface sets the smooth baseline. The atmosphere and nearby gas remove specific colours. The remaining mix shifts the apparent hue even when the temperature stays fixed. The scene begins near a star where the limb looks softly shaded. Above the limb, a thin atmospheric layer glows faintly in scattered light. The layer is not uniform. It forms a gentle stratification. Denser bands sit lower, thinner bands sit higher. Along the limb, the line of sight passes through more of this layered gas. That longer path creates a darker ring in certain colours. The ring is subtle. It is a physical edge effect. It changes the disk's colour gradient from centre to rim. The next unlock follows from selectivity. Gas does not dim all colours equally. Atoms and molecules absorb at particular wavelengths. A term arrives and stays brief. Absorption line means a narrow wavelength removed by gas. The definition stays short. The example becomes visual. A smooth ribbon of light develops thin notches. The reason it matters is calm. Those notches reveal composition. They also tilt the balance inside the visible band. That tilt can nudge the star's apparent colour. A slow everyday analogy carries the idea without repeating earlier ones. It resembles a piece of lace held over a bright window. The window remains bright. The lace removes light in a patterned way. The pattern is not random. It follows the weave. In the same way the gas removes light at specific wavelengths set by its internal structure. The first small payoff lands. Many tiny notches can add up to a visible tint when they cluster in one part of the spectrum. If absorption removes more blue than red, the star looks warmer. If absorption removes more red than blue, the star can look slightly cooler. The physics is quiet. It is subtraction, not addition. The journey moves from the star's atmosphere to gas between stars. A faint sheet of gas lies along the line of sight. The sheet is almost invisible except for how it edits starlight. The sheet has a soft boundary. It is thicker in the centre. It thins outward. That thickness gradient creates a gentle colour gradient across a field of background stars. Unlike dust, the gradient is not smooth across all colours. It is more patterned. Some wavelengths are removed strongly. Others pass almost unchanged. The second payoff arrives. This difference provides a way to tell gas from dust. Dust tilts the whole spectrum smoothly. Gas creates features. Even when those features are too fine to see directly, they change the way colour compares across multiple bands. The narrative deepens with one safe number that anchors scale. A typical absorption line can be narrower than about 1 nanometer. That is far smaller than a grain of dust. The comparison stays every day. It is like removing one hair from a thick brush. The brush still looks full, yet repeated removal in the same region changes the brush's shape. The scale shift follows. A line that narrow is set by atomic structure on the scale of electrons. The same line can be imprinted on light that travels for years across space. Microphysics writes on a cosmic message. The next visual anchor forms as a spectrum imagined as a calm shoreline. The baseline glow is a smooth beach. Absorption lines are small indentations. A cluster of lines forms a bay. A broad molecular band forms a wider inlet. The shoreline image stays gentle and unique. It makes the idea tactile without touching any human object. The third payoff lands. A star with the same temperature can look different depending on which wavelengths are removed. 2 stars can share the same dust path. One still looks warmer because its own atmosphere absorbs more in blue. Another looks cooler because its absorption pattern differs. The source matters again. The journey reaches a limit of intuition. Colour as seen by the eye averages over many details. Narrow lines can be too fine for perception. The mind then treats the star as a single hue. That single hue hides structure. The limit of observation becomes specific. If a signal is measured in broad bands, only narrow lines blur into the bands. The measurement cannot identify which elements cause the tint. If the star is faint, noise can swamp small differences between bands. If the star is unresolved limb path length, effects blend with the center. The ring-like absorption near the limb becomes an average. The result can mimic dust reddening or temperature change. The uncertainty is not a flaw. It is a boundary set by resolution and photon count. The scene slows back to the limb. The layered atmosphere creates a faint darkening in certain colors near the edge. The edge looks slightly warmer because the longer path removes more blue in those wavelengths. The fourth payoff arrives. The limb therefore becomes a natural amplifier of absorption. The geometry stretches the path through gas. That makes small absorptions matter more at the rim. In a resolved disk, this creates a subtle color map. In an unresolved point, it creates a small shift of the average color. The narrative remains calm. No dramatic changes are needed. A few missing threads can change the balance. The closing transition stays soft. Gas carving is now established as a selective editor of starlight. The next step deepens into molecular bands that can become wide and strong in cool atmospheres. Those bands push some stars toward unusually deep reds without requiring more dust. Some stars look deeper red than temperature alone would suggest. Broad molecular bands in cool atmospheres remove large parts of blue and green light, leaving a heavier red balance. The first unlock is calm. Molecules do not need to dominate the whole atmosphere. Molecules only need a cool extended layer where light travels through a long path. The scene opens near a cool star with a wide disk. The center glows warm and steady. The limb fades into a soft rim. Above the rim, a faint atmospheric shell appears as a slightly darker ring in certain colors. The ring is not a line. It is a gradient that thickens toward the limb because the line of sight skims through more gas. A quiet physical detail holds the view. The atmosphere is layered. The lower layer is denser. The upper layer is thinner. In between, small changes in temperature and pressure allow molecules to persist. The next unlock follows from how molecules absorb. Atomic lines are narrow. Molecular absorption often forms broad bands. A term appears once and stays brief. Molecular band means a wide range absorbed by molecules. The definition stays short. The example becomes image-based. A smooth ribbon of light develops wide, darkened valleys rather than thin notches. The reason it matters is direct. Wide valleys can shift a star's overall color. They can also hide the true thermal slope underneath. A slow everyday analogy carries the idea without repeating earlier ones. It resembles a sponge pressed lightly against a wet ink wash. The wash is smooth at first. The sponge lifts ink in wide patches. The paper remains. The pattern of missing ink changes the overall tone. The same happens with starlight. The baseline glow remains thermal. The band absorption lifts light away in wide regions. The first small payoff lands. A star can be cool and still not look extremely red. Deep red often appears when broad bands remove much of the shorter visible light. That removal is stronger when the atmosphere is extended. An extended atmosphere increases path length. The same molecules then have more opportunity to absorb. The journey moves along the limb where path length is longest. The limb becomes a natural amplifier. The disk edge shows a slightly deeper tint than the center. The difference is gentle. It is a measurable gradient in principle. The second payoff arrives. A point source blends center and limb. The blended color can look redder than any single patch. The reason is geometry. Limb paths weight the absorption more than the simple disk area suggests. The scene widens to a faint outflow around the star. A slow wind carries gas outward. The outflow is not a jet. It is a nearly spherical drift. The drift forms a soft shell that thickens in places and thins in others. The shell creates a faint shadow against the background field. The shadow is not uniform across colors. It is stronger where molecular bands absorb. The third payoff lands. Molecular absorption can act beyond the immediate photosphere. It can color the surrounding halo. It can also create a redder aureole that makes the star feel larger and softer. The physical detail stays clear. The halo has layers. The inner halo is denser and darker. The outer halo is thinner and more transparent. The boundary between them is gradual. The narrative reaches one safe number. Molecules tend to persist when temperatures drop below about 4,000 Kelvin in the outer layers of a star. The comparison stays gentle. It is like the difference between hot steam that keeps separating and cooler air that allows mist to form. The point is not water. The point is stability. Lower temperatures allow bound structures to survive. The scale shift follows naturally. The binding of molecules is set by tiny energy steps. Those tiny steps can reshape the colour of a giant atmosphere that spans distances larger than many planetary orbits. Microstructure shapes macro appearance. The next checkpoint introduces a limit of intuition. It is tempting to read deep red as a single thermometer. That intuition fails when broad bands and dust reddening overlap. The colour can be produced by cooler thermal emission, by molecular beads, or by dust along the path. The limit of observation becomes specific. If only broad colour bands are measured, molecular valleys can hide inside the bands. The measurement cannot distinguish a tilted smooth slope from a carved slope. If the star's faint noise blurs the difference between a valley and a tilt. If the disk is unresolved, limb amplification is lost into an average. A spectrum with enough resolution helps. Yet even spectra have limits when the star is dim or when the bands overlap. The scene slows into a calm imagined shoreline of light. The baseline spectrum is a smooth coast. Molecular bands are wide coves cut into that coast. Each cove removes a stretch of brightness. The waterline of the spectrum recedes in those regions. The fourth payoff arrives. Where the coast is cut away, the remaining light shifts redward, because the blue and green contributions shrink. The star's redness can therefore exceed what temperature alone would suggest. The effect is subtraction, not addition. No extra red is created. Less blue remains. The narrative deepens with the second concept that stays within the limit. Molecular bands depend on temperature and density. In denser layers, collisions broaden features. In thinner layers, features can be more structured. The overall colour still reflects the integrated result through layers. The fifth payoff lands gently. A star's atmosphere acts like a stack of translucent sheets. Each sheet removes a little light in certain ranges. The full path adds those removals. The final spectrum becomes a carved version of a smooth baseline. The close remains soft and forward-looking. Molecular bands have now been established as wide sculptors of starlight in cool environments. The next step turns toward carbon-rich and dust-forming cases where outflows add another filter. That filter can push reds into even deeper tones without changing the core thermal story. Some stars appear red as if light has passed through a smoky curtain near the source. The key is fresh dust forming in an outflow that filters the spectrum on the way out. The first unlock is calm and direct. Dust can be created close to a cool star and can redden its light before that light meets any distant cloud. The scene opens around a cool evolved star that sits inside a faint expanding shell. The shell is not smooth. It shows arcs and clumps. A few denser knots appear as soft dark spots against the glow. Between knots, the shell is thinner and more transparent. The star itself looks warm. The surrounding shell looks warmer still, with a gentle gradient that deepens along the thicker arcs. This gradient is a physical map of column density. Where the path through dust is longer, the colour shifts more. At this distance, light behaves as a beam leaving a lantern inside fog. The lantern stays the same. The fog edits the beam. The next unlock follows from timing and location. Dust formed near the star starts filtering immediately. That means even nearby directions see a reddened source. The path length inside the shell changes with the angle. Along the line of sight that grazes the shell edge, the path is longest. Along the line of sight through a thinner gap, the path is shorter. The colour therefore varies across the halo. A slow visual anchor forms as a pair of faint rings around the star. The rings are not solid. They are broken arcs that suggest pulses in outflow. Each arc has a brighter inner rim and a dimmer outer fade. The brighter rim marks slightly higher density. The dimmer fade marks dust dispersing outward. The first small payoff lands. Ring-like arcs imply that dust creation can be episodic. When the outflow density rises, more dust forms. When it drops, the shell becomes clearer. The light therefore carries a record of past conditions. The record is not written in words. It is written in layered opacity. A gentle everyday analogy carries the idea without repeating earlier ones. It resembles a slow puff of flour released into still air. The flour cloud spreads. It forms thicker folds and thinner gaps. Light passing through those folds warms and dims. Light passing through gaps stays clearer. The analogy is about uneven density. It explains why halo color can be patchy. The journey moves closer to the dust formation zone in concept. Near the star gas cools as it expands. When the temperature and density allow solid grains can condense, a term appears once and stays brief. Condensation means solids form from cooling gas. The definition stays short. The example stays image-based. Invisible vapor becomes visible haze when conditions cross a threshold. The reason it matters is calm. The new grains increase extinction. They redden the outgoing light and can hide the inner layers from view. The second payoff arrives. A star can look unusually red even if its surface temperature is only moderately cool. The near-source dust steepens the reddening. It also changes the apparent brightness. The star can seem more distant than it is because the dust removes light. That removal can be uneven. One direction can be clear, another direction can be thick. The halo then becomes a map of orientation and structure. A scale shift follows without strain. The grains are smaller than a cell. The shell spans distances comparable to a system scale. The filtering happens within a short travel time near the star. Yet the imprint persists as the light continues outward for years. Micro-sized grains shape a macroscopic appearance. The narrative reaches one safe number. The shell can expand at about 10 kilometers per second. That is like the speed of a fast jet stream, but stretched across a vast scale. The number anchors motion without detail. The physical scene changes slowly. Over a year, the shell moves outward by a small fraction of its radius. The arcs drift. The gaps widen. The third payoff lands. Because expansion is slow, the halo preserves its layered structure for long spans. The rings do not vanish quickly. They soften. They blend. Yet their gradients remain readable as long as dust stays intact. The journey now adds a limit of intuition. A very red star behind dust can be mistaken for a very cool star without dust. The mind reads color as temperature. Near-source dust breaks that shortcut. The limit of observation becomes specific. If the star is unresolved, the halo and the star blend into one point. The measurement then mixes direct starlight and scattered halo light. The mixed color can shift depending on aperture and seeing. If only broad color bands are used, dust reddening and molecular bands can overlap. The bands cannot tell which layer causes the redness. A spectrum helps, yet even spectra face limits if the star is fainter, or if dust adds a smooth tilt that hides beneath broad molecular valleys. The scene slows into a shadowed wedge behind one dense knot. The knot blocks more blue than red. The wedge looks like a soft triangular shadow that fades outward. The edges of the wedge are feathered. That feathering shows that the knot is not a hard clump. It is a gradient of density. The fourth payoff arrives. The shape of the shadow reveals geometry. A compact clump creates a sharper wedge. A diffuse clump creates a broader wedge. The halo therefore encodes structure without any direct imaging of grains. Light behaves as a tracer of density. The narrative deepens with a second concept that stays within scope. Scattered light can return some blue into the line of sight. The halo can appear less red than the direct beam from behind the thickest dust. This can create a counterintuitive effect. The star core looks deep red. The surrounding halo looks paler. The fifth payoff lands. That contrast is a clue that both absorption and scattering are present. Dust does not only remove light, it also redirects it. The balance between removal and redirection depends on grain size and wavelength. The details can vary. The broad behaviour stays consistent. Blue is more affected, red is less affected. The closing transition remains soft. Near-source dust now stands as a strong explanation for dust-filtered star colours and patchy halos. The next step moves toward environments where surrounding nebular light can add its own colour and confuse the palette further. The path remains gentle and stable. A star's colour can be nudged by the glow of its surroundings even when the star itself stays unchanged. The key is nearby gas and dust that scatter and emit light in specific colours, blending with starlight in the same patch of sky. The first unlock is calm. Some blue haze is reflected starlight. Some red haze is gas emission. Both can bias the apparent colour of a nearby star. The scene opens in a region where faint mist fills the darkness. The mist forms arcs and sheets. Its edges are feathered. A pale star sits near the boundary of a blue-tinted veil. Farther away, a thin crimson arc curves like a quiet crescent. The boundary between blue mist and clear space is not sharp. It fades through a gradient. That gradient is a physical clue that scattering strength changes with dust density and grain size. The journey begins with the blue veil. Blue reflection appears when dust scatters short wavelengths efficiently. The veil does not create new blue light. It redirects existing light from nearby hot sources. The next unlock follows. Scattered light can enter the line of sight from angles that direct starlight does not occupy. This adds a faint blue component around a star. The star can look slightly bluer or slightly whiter depending on the blend. A slow everyday analogy keeps it gentle and new. It resembles a quiet pool that shows a patch of sky colour on its surface. The pool water does not become sky. It redirects skylight into the eye. In the same way dust redirects blue light into the observer's direction. The first small payoff lands. A star near blue reflection can look cooler than it truly is. The reflection adds short wavelength light in the same area. If the star is unresolved from the haze, the measurement merges both. The star's true thermal slope is still present. The environment adds a glaze on top. The scene shifts towards the crimson arc. This arc is not reflected starlight. It is emission from gas. Gas can glow when it is ionized and then recombines. A term appears once and stays brief. Recombination glow means gas emits light after electrons rejoin ions. The definition stays short. The example becomes visual. A thin shell of gas shines along its densest edge. The reason it matters is direct. The emitted light often concentrates in specific visible colours which can add a reddish tint near stars. The second payoff arrives. A star near a red emitting arc can look warmer than it truly is. The arc adds red light that the star did not produce. The blend depends on geometry. If the star lies behind the arc can also absorb and redden. If the star lies beside the arc can add emission without much absorption. The physical detail remains clear. The arc has a bright rim where density is higher. It has a dim interior where gas is thinner. It has a fading outer edge where the shell disperses. The journey now adds a scale shift. The glowing arc can span distances larger than a system scale. The atomic processes that produce the glow occur on scales smaller than a molecule. Micro events produce a macro ribbon across the sky. The narrative reaches one safe number. A typical emission line can be narrower than about 1 nanometer. That is like adding a thin stripe of colour to a broad paint wash. The stripe can still influence the final hue when it is bright. The comparison stays calm and everyday. The third payoff lands. A narrow, strong emission feature can add noticeable redness even when it occupies a tiny slice of wavelength. When many faint stars are measured in broad bands that stripe can shift the band average, the result can make stars near emission appear systematically warmer. The scene slows into a mixed region where blue reflection and red emission overlap. The mist is layered. A pale blue sheet lies in front. A dim red filament sits behind. The overlap makes a violet-like impression in places. The edges of each layer are feathered. The overlap zone shows a gentle gradient. The fourth payoff arrives. A star seen through overlapping layers can show a complex colour that does not correspond to any simple temperature. The colour becomes a sum. It includes direct starlight, it includes scattered light, it includes emitted light. The sky becomes an optical mixture rather than a single beam. A limit of intuition follows. The mind wants colour to mean temperature alone. In such mixed regions that shortcut fails, the limit of observation becomes specific. If the star cannot be separated from surrounding haze due to resolution limits, the measured colour includes background. If the background varies across small angles, subtracting it becomes uncertain. If only broad bands are used, narrow, emission lines can hide inside a band and bias it. If the star is faint, noise can make the background subtraction unstable. A signal would then carry a blended colour that is not uniquely invertible to temperature. The scene returns to the star near the blue veil boundary. The star core remains steady in brightness. The surrounding haze shifts gently with position. A faint gradient of blue intensity flows across the frame. The fifth payoff lands. The gradient itself can be used as a clue. Where the haze is strongest, a star's measured colour shifts most. Where the haze thins, the star returns closer to its intrinsic colour. This offers a way to disentangle environment from source, at least statistically. The narrative deepens with one more physical detail. Reflection tends to be smoother and broader. It follows dust distribution. Emission tends to trace denser gas edges. It forms rims and filaments. Their shapes differ. Their gradients differ. Their influence on star colours therefore differs in pattern. The close remains soft. Environment has now been established as an additive and subtractive editor of star colour. The next step moves toward motion and subtle shifts where wavelength itself slides due to velocity. That shift is small but measurable, and it's a new kind of colour bias, without changing dust or chemistry. A star can shift its colour slightly because motion stretches or compresses its light. The effect is a wavelength shift that moves spectral features and can nudge the overall balance in a measured band. The first unlock is calm. Motion does not change the star's temperature. Motion changes how wavelengths are received along a line of sight. The scene opens on a quiet pair of stars orbiting a shared centre. The pair forms two steady points. A faint oval pattern is suggested by their repeated positions over time. The space around them is dark and clear, yet the light from each point is not identical from one moment to the next. Along the orbits, the component moving toward the observer sends slightly compressed wavelengths. The component moving away sends slightly stretched wavelengths. At this distance, light behaves as a spring that is gently squeezed and gently relaxed. The spring image stays soft. It avoids intensity. It conveys that the spacing between wave crests changes. The next unlock follows from where the shift matters most. The broad thermal spectrum is smooth. Small shifts barely change its overall shape. Narrow absorption and emission features can move across a filter boundary. That movement can change the measured colour in a band. A term appears once and stays brief. Doppler shift means wavelength changes due to relative motion. The definition stays short. The example becomes simple. A pattern on a ribbon slides left or right. The reason it matters is direct. When the pattern includes deep line sliding, changes how much light falls into a chosen band. The first visual anchor forms as a quiet imagined spectrum. A smooth baseline rises and falls. Across it sit thin dark notches. The notches drift slightly back and forth with orbital phase. Most of the time the drift is too small for the eye. Yet for precise measurements it changes the balance. The first small payoff lands. Two stars with the same temperature can show different measured colours at different times if a strong line sits near a band edge. When the line shifts into the band dims. When it shifts out, the band brightens. The colour index changes even though the star stays constant. The journey moves closer to the orbital geometry. The line of sight velocity changes smoothly over the orbit. It is near zero at the side points. It is highest when the star moves directly toward or away. The shift therefore cycles in a calm rhythm. The second payoff arrives. This rhythm can be used to detect motion even when the stars are not resolved. The light carries a periodic slide of lines. The slide is a fingerprint of orbit. The scene widens from a binary pair to a larger region where many stars drift within a cluster. Each star has its own motion. Their motions spread the lines slightly when their light is averaged. The average then looks softer. The notches become shallower. The third payoff lands. When many moving stars blend, the detailed spectrum can look smeared. That smearing can reduce the apparent impact of individual lines on colour. The blend can therefore appear more neutral than any single spectrum. A scale shift follows gently. The wavelength shifts involve changes far smaller than a dust grain. The motions that cause them involve orbits spanning distances larger than many planetary paths. Micro shifts in wavelength encode macro motion over years and centuries. The narrative reaches one safe number. A typical stellar radial velocity in a cluster can be about 10 kilometers per second. That is like the speed of a fast storm front but in empty space. The number anchors the magnitude without arithmetic. At that speed, the Doppler shift in visible light is small. The eye will not notice. Instruments can notice if resolution is high. The next visual anchor forms as a calm colour band filter imagined as a window frame. The drifting spectral line is a narrow shadow that slides across the frame. When the shadow overlaps the frame, less light passes. When it slides off, more passes. The fourth payoff arrives. A small slide can change a measured band more than expected if the line is deep. This explains why motion can mimic a subtle colour change. It does not repaint the spectrum, it repositions the carved features. The journey now adds a limit of intuition. It is tempting to treat any colour change as a change in temperature or dust. That shortcut fails for precise band measurements. The limit of observation becomes specific. Detecting Doppler shift requires sufficient spectral resolution. If the resolution is too low, lines blur together. Their motion becomes invisible. If the signal to noise is low, tiny shifts are lost in noise. If the star is blended with neighbours, the lines of many velocities overlap. The result is a smeared average that hides motion. A signal would then carry only a broad colour, not the sliding details. The fifth payoff lands gently. Even when Doppler shifts are small, their presence explains some scatter in colour measurements across time. It also explains why narrowband filters can show variability not seen in broadband. The variability is not a physical change in the star. It is a mapping change between spectral features and filter edges. The narrative deepens with a second concept that stays within scope. Rotation can broaden lines. Broader lines are less sensitive to small Doppler shifts across a filter edge. Narrower lines are more sensitive. This provides a quiet expectation. Fast rotation can smooth out the band effect. Slow rotation can preserve sharper notches that slide more distinctly. The scene returns to the binary pair. The points maintain their calm orbit. The wavelength notches drift back and forth with the same quiet regularity. The close remains soft. Motion has now been added as a subtle editor of star colour in measured bands. The next step turns towards stars with stripped layers and strong winds where spectral features and continua change more dramatically. The transition remains gentle and stable. Some of the bluest starlight comes from stars whose outer layers are stripped thin and intensely hot. Their colour is set by a hard blue-leaning thermal slope and by strong winds that sculpt the spectrum with broad features. The first unlock is calm. Extreme blue-white can be both temperature and filtering by an outflow. The surface sets the baseline. The wind reshapes which wavelengths escape most easily. The scene opens on a compact, brilliant star wrapped in a translucent envelope. The envelope is not a shell with a sharp edge. It is a graded haze that thickens toward the centre. Its outer boundary fades smoothly into space. Within the haze, a faint ring of slightly higher brightness circles the star. The ring marks a denser zone in the flow. It looks like a soft collar. It has no hard boundary. The collar's gradient creates a gentle brightness step. That step changes how the star's colour blends with its surroundings. At this distance, light behaves as a blade of pale flame seen through moving mist. The flame image stays quiet and non-human. It conveys intensity without sound. The next unlock follows from two ideas working together. The star is very hot, so its thermal emission leans strongly towards short wavelengths. The wind is fast and ionized, so it imprints broad absorption and emission structures on top. A term appears once and stays brief. Stellar wind means a continuous outflow of gas from a star. The definition stays short. The example becomes visual. A steady stream carries material outward in layered sheets. The reason it matters is direct. The outflow changes which wavelengths escape. It can deepen some troughs and fill others with emission. The first visual anchor forms as a spectrum imagined as a pale ridge. The ridge rises steeply into blue. Across it sit wide dim valleys rather than only thin notches. The valleys are smooth because the wind's motions broaden features. The first small payoff lands. Broad wind features can make an already blue star look even bluer in some bands because they remove more light on the red side than on the blue side. In other cases, emission can brighten selected regions and shift perceived whiteness. The direction depends on where the features sit relative to the visible window. The journey moves into the outflow geometry. Near the star, density is higher. Farther out, density falls. The wind becomes more transparent. The collar-like ring marks a region where the flow is denser, or where ionization changes rapidly. That ring can scatter some light back. It can also absorb in certain ranges. The second payoff arrives. A star can appear surrounded by a faint bluish veil that is not dust reflection. It is wind material scattering the star's own blue heavy light. The veil's colour follows the baseline slope. It looks pale and cold. The narrative adds one safe number. The wind speed can be around 1,000 kilometers per second. That is like crossing a large world in about a minute, but in empty space. The number anchors extremity while staying order of magnitude safe. The scale shift follows. The wind is driven by radiation interacting with atoms. Those interactions occur on atomic scales. Yet the resulting flow shapes a region many times larger than the star itself. Micro-level absorption helps accelerate macro-level motion. The journey introduces a gentle, everyday analogy that stays new. It resembles fine sand carried by a strong breeze across a smooth dune. The dune shape is the baseline. The moving sand changes the surface texture. Small ripples appear. Some parts are scoured. Some parts are piled. The underlying dune remains. The analogy is about shaping, not about force on people or objects. The reason it matters is calm. The wind sculpts the escaping spectrum while the thermal slope remains the foundation. The third payoff lands. This helps explain why some blue-white stars look oddly featureful in measured colours. Two equally hot stars can have different apparent hues if their winds differ. A denser wind can carve deeper valleys. A thinner wind can leave a cleaner slope. A change in ionization can move where the carving occurs. The scene slows into the translucent envelope again. The envelope shows faint striations. The striations are not lines. They are smooth bands of slightly different opacity. The bands drift outward. Their edges are feathered. This physical layering creates a subtle brightness gradient. It also creates a subtle color gradient because the wind absorbs and emits differently across wavelength. The fourth payoff arrives. The star's color can vary across the halo. The core looks intensely pale. The outer veil looks slightly warmer, where blue is scattered away more than red. The effect remains small but real. The narrative now adds a limit of intuition. Extreme blue-white can be mistaken for a simple indicator of temperature alone. Winds can bias band measurements by moving and broadening spectral features. The limit of observation becomes specific. Broadband color indices can miss the distinction between a clean thermal slope and a wind-sculpted slope. If the spectrum is not resolved, broad valleys can masquerade as dust reddening or as a different temperature. If the star sits in a crowded field, blending can wash out the wind signature. If the signal is faint noise, can hide subtle curvature in the slope. A signal would then deliver only a simple blue-white color, while the underlying physics remains richer. The fifth payoff lands gently. Wind effects also connect color to evolution. Stripped layers imply late stages for massive stars. The color therefore hints at a life history without needing any human context. The hint remains soft and indirect, the close stays gentle. The most extreme blue-white colours arise from hot surfaces and from winds that sculpt what escapes. The next step widens to how star colours evolve over time and across populations. It follows how clusters show colour sequences shaped by age, mass and intervening material. A cluster of stars can display a whole palette at once, as if colour is arranged along a quiet path. The key is that mass and age set surface temperature, while dust and gas add gentle biases along some sight lines. The first unlock is calm. In a single cluster, blue-white stars are usually hotter and shorter lived. Redder stars are cooler or later in their lives. The scene opens on a loose star cluster against a dark field. The stars are not evenly spread. They form a mild concentration toward the centre. Around that centre, a faint haze traces a soft oval. The haze has a gradient. It is thicker on one side and thinner on the other. Across the cluster, star colours change subtly with position. The bluest points concentrate near the brighter core. Warmer points scatter more widely. A few deep red points sit near the thick haze edge. The physical detail is clear. The haze edge is feathered. It creates a gentle boundary where colours shift more. At this distance, light behaves as many separate threads passing through slightly different lanes. The next unlock follows from the internal sequence. Stars of higher mass burn hotter. They appear blue-white. They also evolve quickly and leave that stage sooner. Lower mass stars stay cooler and longer lived. They appear more yellow or red. A term appears once and stays brief. Main sequence means the long stage of steady core fusion. The definition stays short. The example becomes visual. The cluster has a band of stars that runs from blue to pale to warm. The reason it matters is direct. That band is a timeline written in temperature and brightness. A slow everyday analogy carries the structure without repeating earlier ones. It resembles a shoreline of pebbles graded by size. Near one end, the pebbles are larger. Toward the other end, they become smaller. The beach is one place. The sizes still sort along a gradient. In the same way, the cluster is one place. The stars still sort by mass and temperature along a pattern. The first small payoff lands. Colour in a cluster is not random decoration. It is a consequence of physics and time. Blue points mark hot surfaces. Red points mark cooler surfaces or later phases. The journey moves closer to the cluster core in concept. Dense regions form more massive stars more often. Those massive stars dominate blue-white light early on. As time passes, the brightest blue stars vanish from the cluster's visible census. The colour distribution shifts. The second payoff arrives. A cluster therefore changes its overall colour with age. Young clusters look bluer, older clusters look warmer. The change is not because stars change colour instantly. It is because different stars remain visible in different stages. A scale shift follows gently. Individual fusion reactions occur in tiny spaces, yet the cluster's colour evolution unfolds over millions to billions of years. Micronuclear processes produce macro colour statistics across a whole group. The narrative reaches one safe number. A typical open cluster can contain about 1,000 stars. That is like a small town of lights but spread across a vast void. The number anchors abundance without strain. With that many members, patterns emerge, even when some stars are hidden by haze. The next visual anchor forms as a soft arc of reddening crossing part of the cluster. The arc is not a line. It is a broad lane with a gradient. Stars behind the lane look dimmer and warmer. Stars outside the lane look clearer and bluer. The third payoff lands. This lane reveals that dust can impose a second colour pattern on top of the cluster's internal sequence. Two stars of similar intrinsic type can appear different because their lanes differ. The cluster therefore contains both an internal map and an external overlay. The internal map is mass and age. The external overlay is intervening material. The journey introduces a second concept that stays within scope. Differential reddening means dust varies across nearby sight lines. The definition stays short. The example remains visual. One edge of the cluster sits behind thicker haze. The other edge sits behind thinner haze. The reason it matters is calm. Differential reddening can blur the cluster's clean colour pattern. It can scatter points away from the expected band. The fourth payoff arrives. This scatter is not merely noise, it is a physical record of dust structure across the field. The feathered boundary and gradient suggest a continuous distribution. The lane's width suggests a sheet rather than a thin filament. The scene slows into a darker pocket where only a few stars shine through. In that pocket, the faintest blue stars vanish first. The visible set becomes redder. The cluster's colour distribution locally shifts. The fifth payoff lands. Dust can create a selection effect. It hides some stars more than others. The observed cluster can appear older or cooler than it truly is if the view favours redder survivors. The narrative now adds a limit of intuition. It is tempting to read the cluster's colours as a single age. That shortcut fails when reddening varies across the field. The limit of observation becomes specific. If membership is uncertain, unrelated background stars can enter the sample and confuse the pattern. If the cluster is distant, crowding blends nearby points and mixes colours. If photometry uses broadbands, only dust and temperature effects overlap. If background subtraction is imperfect, faint haze light can bias colours. A signal would then carry a smeared diagram rather than a clean sequence. The scene returns to the full cluster view. The central concentration remains steady. The haze lane remains as a soft diagonal. Blue-white points sparkle more in the clearer half. Warm points populate both halves. The close remains soft. Clusters show that star colours are both intrinsic and environmental. The next step widens from clusters to entire galaxies where dust lanes, star formation and aging populations create large-scale colour gradients across spiral arms and bulges. A galaxy can look like two different objects at once, blue along its arms and warmer toward its centre. The key is that young hot stars cluster where gas is dense, while older stars dominate the bulge and dust lanes quietly redden parts of the disk. The first unlock is calm. Colour gradients across a galaxy are not paint. They are an atlas of populations and intervening material. The scene opens on a spiral galaxy seen at a slight tilt. A bright central bulge glows with a smooth honeyed tone. From the bulge spiral arms unwind in soft arcs. Along each arm, patches of pale blue gather like scattered frost. Between arms, darker lanes cut through the disk. These lanes are not lines. They are bands with feathered edges. Their darkness deepens toward the mid-plane and fades outward. The physical detail is immediate. Dust lanes show a gradient and a shadowed spine. The spine is darkest where the path through the disk is longest. At this distance, light behaves as layered sheets passing through a thin, uneven veil. The next unlock follows from star formation geography. Gas and dust concentrate in arms. Their new hot stars appear. Hot stars shine blue-white. Their light also makes nearby gas glow in blue-leaning and reddish accents. Older stars spread more smoothly. They dominate the bulge with warmer tones. A term appears once and stays brief. Stellar population means a group of stars with shared ages and traits. The definition stays short. The example becomes visual. The bulge is a smooth blend. The arms are patchy and clumped. The reason it matters is direct. Patchiness signals youth and ongoing formation. Smoothness signals age and long mixing. The first visual anchor is the boundary where an arm crosses a dust lane. The arm's blue patches dim and warm abruptly along the lane. The lane's edge is soft. The change is not a sharp cut. It is a gradient. The first small payoff lands. Dust lanes do not only darken, they also tilt colours warmer by removing more short wavelength light. This can make an arm look less blue on one side than the other. The same arm can therefore show two apparent temperatures depending on viewing through the disk. The journey moves inward toward the bulge. The bulge light is smoother. Its colour is set by many cooler stars. These stars are not necessarily cold, they are simply less hot than the youngest massive stars in arms. Their combined light shifts toward yellow and red. The second payoff arrives. A bulge can look warm even when it contains some hot stars because the luminous budget is dominated by a large population of cooler members. The warm tone is an average, not a single surface. A scale shift follows gently. Individual stars contribute tiny points, yet their summed light makes a continuous glow across thousands of light years. Micropoints become macro gradients. The narrative reaches one safe number. A spiral galaxy can span about 100,000 light years. That is like placing a light and waiting through a long geological age for it to cross. But in space the measure is distance, not time. The number anchors scope. Within that span the colour map changes smoothly from centre to outskirts. The next visual anchor forms along the outer disk. The starlight there is faint. The arms are thinner. The dust lanes are less heavy. The background sky shows through more. The third payoff lands. Outer regions can look bluer not only because of young stars, they can also look bluer because there is less dust to redden the light. Lower dust column means a cleaner view of the intrinsic spectrum. The journey introduces a gentle everyday analogy that stays new. It resembles a layered quilt seen under uneven lampshade fabric. The quilt has different patches. The lampshade adds a warm tint in some directions and a clearer tint in others. The quilt does not change. The viewing tint changes. The analogy is about overlay. It explains why galaxies can have internal colour structure plus a dust filter on top. The narrative adds a second concept that stays within scope. Inclination changes path length through the disk. A more edge-on view increases dust effects. A more face-on view reduces them. The fourth payoff arrives. The same galaxy can appear warmer overall when viewed closer to edge-on. The longer path through the mid-plane removes more blue light. The dust lanes then look thicker and darker. The arms look less contrasted in blue. The bulge can appear even more dominant. The scene slows into a narrow dust lane crossing the bright centre. The lane creates a dark bite across the bulge. The bite is not symmetric. One side of the bulge is more obscured. The lane's edge shows wisps and filaments. The filaments fade into transparent space. The fifth payoff lands. This asymmetry reveals depth. One side of the disk lies in front, the other lies behind. Dust is a three-dimensional veil. Its shadow reveals orientation without any motion. The narrative now adds a limit of intuition. It is tempting to read a galaxy's colour as a single age and a single metallicity. That shortcut fails when populations mix and dust varies. The limit of observation becomes specific. If resolution is low arms and bulge blend and the colour becomes a single average. If the galaxy is far small, blue patches merge into a smooth blue haze. Dust lanes then become hard to separate. If only broad bands are used emission from gas, can bias colours in arms. If background subtraction is uncertain, faint sky glow can shift the outer disk colours. A signal would then carry a simplified gradient that hides the layered causes. The close remains soft. Galaxy colours are now framed as a map of youth in arms, age in bulges and dust, as a quiet editor. The next step moves outward as to the oldest light, where distance itself reddens the spectrum, and where colour becomes a tool for cosmic scale, not only for local physics. A very distant galaxy can look warmer even if its stars are not especially cool, because expanding space shifts its light to longer wavelengths. The key is cosmological redshift, which slides the entire spectrum and can move blue light out of visible bands. The first unlock is calm. Distance can act like a gentle colour filter. It does so without dust and without changing the source. The scene opens on a deep field sprinkled with faint galaxies. Most are small smudges, a few are stretched arcs with smooth curves. The arcs have bright rims and dim interiors. Their edges show a gradient. The brightness falls inward like a slow fade. Around them, the background is nearly black. In the centre of one arc, the colour looks slightly warmer than the rim. The physical detail is clear. The rim is sharper. The interior is softer. The gradient suggests light being redistributed by lensing and by the source's own structure. At this distance, light behaves as a long ribbon that is gently pulled while it travels. The ribbon image stays quiet. It conveys stretching without forceful language. The next unlock follows from one idea. As the universe expands, the wavelengths of travelling light lengthen. This shifts features to redder positions. The star's intrinsic spectrum remains the same at emission. The received spectrum is slid. A term appears once and stays brief. Redshift means light arrives at longer wavelengths than emitted. The definition stays short. The example becomes simple. A painted pattern on a rubber band spreads out when the band is stretched. The reason it matters is direct. If a blue feature slides into a green band, the measured colour changes. If ultraviolet slides into visible, a galaxy can appear bluer than expected in one filter and redder in another. The first visual anchor forms as a set of broad filter windows imagined as three adjacent doorways. A smooth spectrum passes through them. The whole spectrum shifts rightward. A prominent break in the spectrum drifts from one doorway to the next. The first small payoff lands. The same galaxy can switch apparent colour categories as redshift increases because the filters sample different parts of its spectrum. This is not a change in the galaxy. It is a change in which slice is being measured. The journey moves closer to the idea of spectral breaks. Many galaxy spectra have a strong change in slope at certain wavelengths due to absorption in stars and gas. When that break crosses a filter boundary, colour indices change sharply. The second payoff arrives. Abrupt colour changes in surveys can reflect a break crossing, not a sudden new physical population. A gentle scale shift follows. The break is set by atomic transitions and photospheric absorption within stars. Those processes happen at tiny scales, yet their signature becomes a tool for mapping distances across billions of light years. Microphysics becomes macrogeography. The narrative reaches one safe number. A redshift of about 1 means wavelengths are roughly doubled. That is like hearing a familiar melody slowed to half speed. But here the change is in wavelength, not time. The number anchors the effect without equations. When wavelengths double, blue light can shift toward green and red. Ultraviolet can shift into blue. The measured colours can reverse expectations. The next visual anchor forms as a faint galaxy that appears as two-toned. One side is slightly bluer, the other is slightly warmer. The boundary is not sharp, it is a soft transition. The third payoff lands. In lensed arcs, different source regions can be magnified differently. If star-forming regions and older regions are magnified in different proportions, the observed colour can vary along the arc. Redshift sets the overall slide. Lensing and internal structure set the local colour texture. The journey introduces a gentle everyday analogy that stays new. It resembles looking at a woven cloth through a set of tinted panes. The cloth has patterns. Each pane selects a different thread colour. Sliding the cloth sideways behind the panes changes which threads align with each pane. The cloth does not change. The sampling changes. The analogy captures filter selection and redshift together. The narrative adds a second concept that stays within scope. K-correction is the adjustment needed when observed bands correspond to different emitted bands at different redshifts. The definition stays short. The example remains calm. A red filter might capture emitted blue light from a distant object. The reason it matters is direct. Without correction, comparisons across distance can misread populations. The fourth payoff arrives. A distant galaxy can appear red in one observed band because that band is sampling its ultraviolet drop. Another galaxy at a different redshift can appear red because it is truly old and dust-rich. Similar observed colour can come from different causes. The narrative now adds a limit of intuition. It is tempting to equate red observed colour with old stars or heavy dust. That shortcut fails at high redshift. The limit of observation becomes specific. Photometry alone can confuse redshift effects with dust reddening. Noise can scatter faint objects between colour bins. Blending can mix colours of neighbouring sources. Low resolution can smear small galaxies into the background. Without spectra, the exact position of breaks is uncertain. A signal would then carry an approximate redshift estimate with broad uncertainty. The fifth payoff lands gently. This is why deep surveys rely on many bands. Multiple bands can bracket a break and reduce ambiguity. The scene returns to the deep field. The arcs remain quiet curves. The smudges remain faint. Yet the palette across the field now reads as distance layered on top of composition. The close remains soft. Redshift is a cosmic colour shift that can masquerade as temperature and dust. The next step settles back toward a gentle resolution that connects all earlier causes from atomic scattering to galaxy-scale gradients into a single calm map of why stars and starlight look the colours they do. A star's colour is not a single label because every path between star and observer adds or removes parts of the spectrum. The key is that temperature sets a baseline while absorption, scattering and distance shift what finally appears. The first unlock is gentle. The sky's palette is a layered story written in light. It begins at a stellar surface and ends after long travel through matter and expanding space. The scene opens on a quiet patch of night where many star colours share the same darkness. One point is deep red and steady. Another is blue-white and sharp. A third looks pale yellow. Between them a faint haze lies like thin smoke, but it is not smoke. It is a low, diffuse glow from dust in the line of sight. The physical detail appears in that haze. It is not uniform. It has a soft edge and a slight gradient. It is thicker in one direction and clearer in another. At this distance, light behaves as a stream that can be thinned by selective loss. The first visual anchor is the subtle dimming around a red star when the surrounding dust thickens. The star's halo is not a hard circle. It's a gentle bloom with a wider wing on one side. The first small payoff lands. Colour and brightness are linked, but not in a simple way. A star can look redder because blue light is removed. It can also look red because its surface is cooler. The same hue can come from different causes. The journey takes a step inward to the source. A hot star emits more short wavelength light. A cool star emits more long wavelength light. This baseline is the simplest layer. It explains why blue-white often signals higher surface temperature, and deep red often signals lower temperature. The second payoff arrives. Even this simple layer is averaged. A star's atmosphere is not a single uniform sheet. It has depth and gradients. Different wavelengths emerge from different depths. This can slightly bias colour. A scale shift follows. The change begins in a thin atmospheric layer that is tiny compared with the star's radius. Yet the integrated effect is visible across distances measured in light years. Small layers shape large impressions. The narrative introduces a first concept with a brief definition. Absorption lines are narrow wavelengths removed by atoms. The definition stays short. The example is calm. A spectrum is like a continuous ribbon with tiny notches. The reason it matters is direct. Those notches can shape broad colour when many overlap. Metals and molecules can create wide bands. These bands can warm or cool the perceived tone. The next visual anchor forms as a slow sweep across a star's spectrum imagined as a smooth hill. Along the hill, shallow valleys appear. Some valleys group together. The grouped valleys carve a broad dip. The third payoff lands. When a broad dip falls within a visible band, the star's colour shifts, even if the temperature stays the same. Two stars with similar temperatures can therefore differ in colour because their atmospheres differ. The journey steps outward into the interstellar medium. Dust grains scatter short wavelengths more efficiently. This makes distant stars look redder than they are. Dust also dims. It acts like a quiet curtain. The fourth payoff arrives. Reddening and dimming travel together. A star can appear both fainter and warmer along dusty paths. The physical detail of dust returns as a lane with a soft border. The border is feathered. The lane shows a central spine that is darker. On either side the darkness fades. This texture matters. It shows that dust is clumpy. Clumps cause uneven colour shifts across small angles. The narrative introduces the second concept with a brief definition. Scattering is light redirected by small particles. The definition stays short. The example is everyday and new. A beam through mist looks whiter from the side, yet the source looks warmer. The reason it matters is direct. Scattering changes what reaches the eye along a straight path. It also adds a faint glow around dense regions. The next visual anchor is a quiet nebular edge. The edge is a boundary where starlight meets dust. The boundary glows faintly. The glow is not uniform. It has ripples and knots. The fifth payoff lands. The glowing edge reveals dust geometry. Where the boundary is sharp, dust density changes quickly. Where it is soft, dust is spread out. The colour shift along the boundary can map density without any instrument shown. The journey then steps farther than dust. Very distant galaxies carry an additional layer. Expansion stretches wavelengths. This moves spectral features into different bands. The sixth payoff arrives. A distant galaxy can appear red because the sampled band now captures a shifted part of the spectrum. This redness can mimic old populations or dust. The scale shift becomes large. Atomic absorption occurs at scales smaller than a grain of sand. Dust lanes span tens of thousands of light years. Redshift is set by the growth of space over billions of years. One impression of colour can therefore combine microphysics and cosmic history. The narrative reaches one safe number. Visible light spans roughly a factor of 2 in wavelength from blue to red. That is like a piano range that is only 1 octave wide, yet it holds many notes of meaning. Within that narrow span, small changes can be decisive. A slight dust increase can nudge a star toward red. A slight shift in band sampling can reclassify a galaxy's colour. The limit of intuition arrives softly. Human perception compresses colour into a few categories. Instruments and models can also compress with broad filters. This can hide mixed causes. The limit of observation becomes specific. Broad bands cannot uniquely separate temperature, dust, and redshift. Faint sources suffer noise that biases colour. Crowded fields blend light from neighbours. Variable extinction across a field can tilt comparisons. Without spectra, the breakpoints and dips are inferred. A signal would therefore carry uncertainty that grows with distance and faintness. The close becomes calm and steady. Star colours are not decorations. They are layered diagnostics. The palette comes from temperature, then from atmospheric absorption, then from dust, then from distance and expansion. The next moment is a soft landing. The sky remains full of quiet points. Each point carries a small story written in the gentle arithmetic of light.